Hi y'all, welcome back to another round of physics, and this video we're going to be looking at 2D motion, and just working a couple of example problems with essentially projectile motion, constant acceleration. So the first thing I'm going to have you do is go ahead, watch the clip from, it's a movie, Rumble in the Bronx from mid-90s, and enjoy. Okay, and we're back. So I've grabbed a screen from the movie, and you notice that this isn't a stuntman. This isn't any wires or any kind of weird stuff. Jackie Chan actually made this jump, which he's known for doing his own stunts. So what we want to do is let's see if we can figure out how fast did Jackie Chan run. So we'll say how fast was, was he running? Okay. Is this some superhuman feat? Is this something that, you or I could do? Let's get some idea here. Now, of course, we want to actually run this problem. It's a free fall problem, constant acceleration. So we better put that, the acceleration here is the acceleration due to gravity. So what we need to do is we need to be able to analyze this photo and figure out what kind of information we can implicitly get that will help us do the physics problem. So one of the first things I note is right here. Here's the balcony that Jackie Chan lands on, and I will stretch it across. And if I notice, okay, and those are roughly about the same height. So we'll say that the floor here is about the floor of that balcony. So he's falling about one story. Okay, so that's the first thing. The other thing I'll notice, and I went and looked this up, is that a standard width of a street, so one lane of traffic on a highway or on a street, is roughly 3.7 meters wide. Okay. So if I assume, I'll make an assumption here. Let us assume that these two buildings are separated by a 2-lane street plus sidewalks. So a 2-lane street would take us up to something like 7.4. Let's say that each sidewalk is about 1 meter to 1.5 meters in width. Okay, so another 3 feet on either side. So at the end of the day, I'm going to approximate this gap as being something about 10 meters. Okay. 2 road widths plus sidewalk. So we'll say that that's about 10 meters or so. Okay. Now, of course, I got that information, the 3.7. I went to the DOT or something like that and just looked it up. But that's something that's fairly standard. Okay. So then the next thing that we're stuck with is we need to find, if we can, how high did he fall from? Now, we could do this a couple of different ways. One way to do it is that we can say, well, wait a minute. Right here is a fence post. Here's a post or a fence to prevent people from falling off the parking garage. Seems pretty reasonable. And here's the front grille of a truck or a car of some sort. You figure, okay, if you're standing outside and you're next to a truck, your parents' SUV, or if you happen to own a big truck or something, I would argue that this grill usually comes up to about, let's say, 1 meter. Okay, it comes up to about your waist, so it's probably about 1 meter tall. Okay. And you could compare with the fence post. You say, well, how high should a fence be so that I don't fall off? Well, it should probably be slightly higher than your waist, and it looks like here, it's probably, if this is truly 1 meter, it looks like this is a 2nd meter. So that fence post is probably about 2 meters tall. So we have that idea. Okay, so this is about 2 meters. If this is 2 meters, right here, Okay. You can visualize. Let's stack a couple more of those. Let's stack a couple more of those. Okay, so I'm going to take this. I'll copy it, paste. So there's a second one. I'll go copy, paste. Here's a third one. Copy, paste. And let's say there's a fourth one. Okay. So if this is 2 meters, we stack about 4 of those and we hit the top of the next story. Now, of course, Jackie had to jump over that fence post, so that's number 1. And second of all, because of the perspective, this dark line actually represents the same height, right? It's the perspective. So I would argue, if we get rid of all of that, we're going to say that this is about 8 meters. Sound good? So now we have quite a bit of information. Let's see what kind of stuff that we can come up with. Now, since I've got it drawn on the picture already, why don't we call this the origin? We'll call that the origin right here. Call that O. And we'll call this, sorry, that's a bit hard to see. Let's see if we can get a little bit better of a color here. We'll call this right here the Y direction. And why don't we call this direction the X direction? Still not a good color. We'll call this the X direction. Okay? In fact, let's go ahead and get rid of the photo. We've got all of the pieces of information that we need. Let's go ahead and get rid of the photo. So now we have some information here that will help us. Okay? Going into our process, let's identify the initial state, and let's find the final. Got it? Good. We'll say initial right when Jackie leaves roof. And final is moment before landing. Okay. And that'll just help us, clarify stuff in our head. And we're gonna, aside from the kind of the distances, and actually you can see now, you see how this arrow is slightly shorter than this arrow. So again, thinking of our scaling, this distance in the vertical direction should be slightly less than in the horizontal direction. Okay, so let's go ahead, and now that we've got our initial and final states, why don't we go ahead and just write down the information that we have here. So let's go ahead, let's get this out of the way. Okay, so for the initial, right up here, there's the initial state. Let's go ahead, and here's the final. For the initial, let's go ahead and just write down all the information we know. So we can say, for example, the initial X position is 0, right above the origin. The initial speed in the X direction is a big question mark. We don't know that yet. The acceleration in the X direction. Okay. What's a good approximation to make here? Help us do the problem. We're going to assume that there is no acceleration in the X direction. Okay? In other words, so we'll assume 0. And usually you'll see this when you see phrases like neglect air resistance. Okay? Or assume no friction. No friction. Okay? And of course, I'll tell the joke in class about, remind me, what's the joke about the farmer? Okay, so if you say the farmer and the physicist joke, remind me, I'll tell you a joke in class. or see the end of this lecture video, I'll put a cartoon up as well. We make this right now, we're applying this assumption because it helps us actually do the problem. We can still come up with a reasonably good estimation, and this helps simplify it so that we can do that estimation. Okay. So these are the x components. Let's go ahead and write the y components down as well. So the y component, we say we start off at 8 meters, and that comes from just looking at the scale of the photograph. The initial speed in the y direction equals. Now, what's a good number to put in here that will help make our lives easier? You got it? I'm going to put in 0. Okay. Again, I am going to assume something here that helps me do the problem. I am going to assume that Jackie runs horizontally. In other words, when he leaves the roof, there's no up or down motion. He's going straight out. Okay. Now, you can watch the video clip. You say, well, he's jumping off a car and all that kind of stuff. Yeah, but I'm just trying to get a rough estimation. I'm trying to simplify this to a point where I can actually do it. Okay? And the acceleration in the y direction, since I've called up positive, see, I've chosen that direction to be positive right there. That means that I will put in negative g. And I'll leave that just in terms of g for right now. Okay. Good so far? Okay. So here is, let me move this out of the way a little bit. We'll just move that. Here are my information. Okay. Let's move that out of the way, and let's move this out of the way. Just so that we have it kind of a nice separation. Now let's go ahead and do it for the final state over here. So right when he lands, okay, we have the x component, final. Well, we had that as 10 meters. We have our speed in the x direction, final in the x direction. That's still unknown. But if we look, if we assume the acceleration in the x direction is 0, what does that tell us about the final speed as compared to the initial speed? They're the same. We'll put a question mark there. And the time of flight, we don't know, so I'll put a question mark there. Bummer. For the y direction, y final, we have 0. The speed final in the y direction, we don't know. And again, the time, we still don't know. Okay. So if you want, I'll put time down twice. Okay. We still don't know those. So here's our information. This is all the information that we have. Now we need to figure out how to run the problem. I'm going to clear off this just so that we have a place that we can work. And let's go at it. Now, steps. We need to find our steps. So let's do this, steps. And the question I'll ask you is, thinking about the process, which motion, the motion in the x direction, the x direction back and forth, or the y direction, which of those motions really determines how long Jackie is in the air for? In other words, the time. It's the motion in the y direction. This motion dictates how long he's in the air for, and during that flight time, this motion dictates how far he travels. So what I really want is, step 1, I need to use the vertical motion, so the y direction information, to find delta t. Or, instead of delta t, I'll call it t final, or t. And then 2, once we have that, we can use the x direction information to find the speed in the x direction. Okay, that's our general process. And if you go back and look at the past video, this is the exact same process we were doing with that ball 1, ball 2 problem. Okay? Except in this case, like I've said and hinted at, you've combined both of those motions into a single object. Okay? So let's go at it. Step 1. Step 1, find t. And what I'll say is I'm looking at y direction. So it's always good before you start the problem to specify which component you're looking at. So here I'm looking at the y direction. And let's take stock. How many, if I look at the y direction variables, how many things don't I know? I don't know my final speed in the y direction, and I don't know my time. So I better choose the equation that doesn't have time and has final speed. Strike that, swap it. I need the equation that has the time and not the final speed. Willy Wonka moment there. Excuse me. So the equation that has the time and doesn't have the final speed, you've probably already got that. Let's see here. V naught in the y direction t plus 1/2 ay t squared. Now maybe this is redundant. Since you've already specified the y direction, maybe these are redundant. I figure it's better to write too much than not enough. Okay? Subscripts are free. Well, we've got everything we need. I'll go ahead and substitute in my 0. So I have my final height is 0 minus my y naught equals my speed in the y direction is 0 plus 1/2. I'll put the g in, t squared, negative g. And I'm working in terms of variables right now. Let's find t. So I will multiply both sides by 2 and divide by negative g. I end up with y naught 2 divided by g equals t squared. And I square root both sides. Now if you pause the video here and you look, this was the exact same expression that we had last time for the time. So that's one of the nice things, is when you work in terms of variables, sometimes you have the exact same equations, even though you have slightly different situations. That's another advantage. So you, instead of going through this, we could have just said, okay, rewind and look at the last video. Let's go ahead and plug in our numbers here. So we have 2 times 8 divided by 9.8 square rooted equals t. And so we come up with a final value, square root of 16 divided by 9.8. I have a final value of something like t is equal to 1.28 seconds. So I'll leave it like that for right now. I'm going to store that in my calculator so that we don't introduce those rounding errors. Okay, see, stored it right in my calculator. If I could figure out how to hold that calculator. There we go. Okay, good. Now it would really be cool, and maybe this is something else, maybe we could put a timer on the video and see how long it actually took in real time. But we'd have to make sure that it wasn't slow mode or anything like that. So that might be something that we could do at the end as a sanity check. So now that we have our time, let's go ahead and proceed to our next step. As promised, our next step is we'll use t to find the initial launch speed. Okay. So now I have this one. We can it's no longer unknown. We can put in, okay, well, time, we know this one. I'll go ahead and write it in here. We said it was 1.28 seconds. 1.28 seconds. Okay. So now we're home free. we can say, okay, well, I need the one that does not involve, well, I guess v final. So I could write delta x is equal to v naught in the x direction t plus 1/2 a t squared. It's always good to start out with the most general equation. Then we go ahead and start substituting. So our final is, we have x final minus 0 equals v naught x t plus 0. No acceleration in the x direction. And we started at the origin in terms of the x motion. Rocking and rolling. Of course, you say, okay, I already knew this. Distance divided by time is equal to the speed. Okay. Let's go ahead. The distance we estimated as being 10 meters. The time we found to be 2.8 meters. And we're home free, x. So 10 divided by this answer. I get something like 7.83 meters per second equals v naught x. There we go. Cool. Now this is certainly doable. This is pretty easy. I mean, a good sprint, not a problem. Okay, so let's go ahead and move on to a different problem here. Again, we're still dealing with 2D kinematics and specifically projectile motion. But I thought, well, let's go for another one. So here's another problem. A baseball player hits a home run over the green monster. In order for a baseball to just clear the wall, at what speed must the ball be hit, assuming it leaves the bat at 30 degrees? Now, for context, the green monster is actually the left field wall at the Red Sox stadium. So this is actually a picture of the green monster, and it's my understanding is it's such a large wall because behind this wall is actually a highway that runs by the stadium, and so they tried to make the wall high enough so that you couldn't hit over it. Now, if we look up some figures, some numbers, it turns out the height of this thing is 11.3 meters. So the height is 11.3 meters. And it's a distance of 94.5 meters away from home plate. So I'll put at 94.5 meters away. Okay. So that's the question. A baseball player hits a home run over the green monster, which is a height of 11.3 meters and 94.5 meters away, in order for a baseball just to clear the wall. Okay, so let's highlight this as a verbal, just clear. Okay, so we're not talking about some monster hit. We're talking about just barely gets over. At what speed must the ball be hit, assuming it leaves the bat at 30 degrees? Cool. Ready to hammer away at this? So I'm going to write down the height and the distance information up here again. I'm just going to copy it down so that when I get rid of everything else, we don't have to worry about keeping it. Okay, there we go. So let's get rid of that, and we will go ahead and get rid of this so it's out of our way. Good. Well, we should probably start with something like an initial and final state. So let's go ahead, and as I write this, you should already be thinking about it. Wow. As I'm writing this, you should already be thinking about what you're putting down here. And final state. So we'll say, okay, just before hitting, or excuse me, just after hitting. Okay. And the final state we'll say just clears the wall. Those would be good initial and final states. Okay. And I assume that you took the time to pause the video and actually come up with those on your own before you started. So next issue is let's go ahead and draw a diagram just so that we can conceptualize what's going on here. So I'll call this right here home plate, and we have some distance. There we go. And while we're at it, I will put in a y-axis. So let's start off with our axes. I'll call this y. I'll call this x, and I'll put home plate right here at the origin. Okay, so I'll call that the origin, and I'll have it as home plate. Home plate. Okay. Now, let's go ahead. I'll use this. There we go. I'll use this to describe where my wall is located. It doesn't have to be anything fancy. Okay. And our final position will be when the ball is just clearing the wall. So right here. Right, just clears it. So our initial, our final. Now let's go ahead and write down the information that we have. Well, for example, we want our x components and our y components. So I'll put x initial is equal to 0. 0. There we are. How about our speed in the x direction? Initial speed in the x direction. We haven't the foggiest idea. Don't know. We do have one piece of information that will help us with that, though. And I haven't drawn it in here yet. Let's go ahead and draw it in now. We are told that, we are told that it is launched at a 30-degree angle. My goodness. There we go. We do have one piece of information, though. We are told that it launches at a 30-degree angle. So I'll go ahead and draw in a line, and I'll put a vector sign over it. I'll put my v naught, and we're told that this is at 30 degrees. That will be particularly helpful for us. Okay. Now, if I know this angle is 30 degrees, here's a question for you. How can I relate the angle, theta, the initial speed, I'll say the magnitude of the initial speed, and the initial speed in the x direction? Got it? Good. This would just simply be the magnitude of the velocity. So I'll put that in here. Magnitude of the velocity, cosine of the angle. Okay, so we're using those trig functions. You can almost see the triangle here. Good. How about the acceleration in the x direction? Well, we make the approximation that it's 0. In other words, we're going to assume right now that air resistance is negligible. Good. How about the y components? Let's go through. Y naught equals... Okay. I think you can make actually one of two arguments here. You could say, well, I'm going to approximate it as 0, which is perfectly fine with me. You could also say, oh, let's say a person's 2 meters tall. When they hit the ball, they're about 1 meter off the ground. And you can do it that way. Okay? So I'm going to leave it right now in terms of variables. I'll just call it y naught. But let's say you know what that value is. And I'll actually run the whole thing in terms of variables. And at the end, if you plug in 0 or if you plug in 1, you can still solve the problem. Okay? How about the initial speed in the y direction? Thinking about what we did in the x direction, we could do the same thing in the y direction. We have v naught, the magnitude of the speed, times sine of the angle. And of course, the acceleration in the y direction, we'll call that negative g. Okay. Again, negative sign because I've called up positive. Someday I'll have to do a problem with down as positive. Just, you'll see it all works out. Okay. Well, now that we've got the initial, let's go ahead and work on the final. And I'll go ahead and do all of these. So we have x final. Well, we're told the distance from home plate. So this should be 94.3 meters. Oh, excuse me, 5. Do what I say, or do what I write, not what I say. And I've seemed to have buggered that up even worse. Okay, 94.5 meters. Okay, so we have that value. How about the final speed? Good, good, good. That's still just the initial speed, right? My acceleration in the x direction is 0. Therefore, my speed doesn't change in the x direction. And the time of flight? Don't know. put a question mark there still. Now let's move on to the y components. You say, okay, well, the final, we're told that it just clears the top of the wall. So just clearing the top of the wall means that it's at 11.3 meters. Okay. V final in the y direction, that's a big question mark, and the t is still a big question mark. So let's go through here, and I'll underline it, say in this wonderful pink. Let's go through and underline the things that we don't know. We don't know the final speed in the y direction, the time of flight, or the initial speed. Okay, so I'll underline that just to keep us aware of what we don't really know. Okay. Very good, very good. So now if I take stock, if I look at this, I'll say, okay, which component do I have more information about? You'd say, hopefully you would say, I think the x direction. Okay. Now, I don't know for sure if that's what came to mind. The other honest way to do this is pick a component, start working through. If you get stuck, try the other component. Okay. So experience here tells me, experience here tells me that I'm going to try the x component first. Okay. So let's go ahead and get rid of all of this. I assume that you have it written down on your paper. So we'll go ahead and get rid of all of this. And I'm going to try the x direction. So looking at the x direction. Oops. Excuse me. Okay. And more specifically, I'm going to try to use the x direction to find the time of flight. Okay. You say, well, why is that? And the answer is, or at least how I would explain it, is what's going to dictate how long this thing is in travel time for is how quickly it can get to the far wall, the green monster. And that is dictated in the x direction. That's at least how I kind of think about it. So let's see if we can come up with a time. Now, unlike your previous example, here we're going to have to actually substitute and solve two equations simultaneously. So you are left with you have to actually work in variables here because you're not going to actually have all of the numbers you need. So how I'm going to start off is I'm going to start off with the one that we know and love. Delta x is equal to v naught in the x direction t plus 1/2 a in the x direction t squared. And you might say, well, why'd you start off with that one? And the answer is that I don't know v naught, v final, either of these values. Okay. So but I want to find t. Okay. So I'm choosing the equation that has t and only has one of these two. Okay. And that's why I chose this equation. Okay. So now the next step is let's go ahead and substitute in our zeros and find an expression for t. Now, I assume you've already done that. Either you're pausing it and doing it, or you've done it and you're continuing on now. Well, this is x final, which we have a value for, minus 0 equals, and here I'll make the substitution, v naught cosine of theta t plus, and then acceleration is 0, so we'll put 0. Good. Now let's find t by itself. So we get x final divided by v naught cosine of theta equals t. And like I said before, we wouldn't be able to do this any other way. If I look, remember, we know a value for x final, we know a value for theta, but we don't have a value for v naught. So these are my two unknowns. Okay? You have two unknowns, you need two equations to solve it. Okay? There's no other way around it. So let's go to the y direction. This is where we're going to get our second equation. We'll get it from our y direction. Okay. And similarly, if we go back and look, we don't know anything about the initial and final speeds. Okay. I'm going to choose the equation that does not have the final speed in it. Namely, delta y is equal to v naught y t plus 1/2 a t squared, and this is in the y direction. And again, I chose this equation because it doesn't have y final in it, and I prefer y naught because I have at least that angle, that launch angle, so that helps me out a little bit. So let's go through and substitute in our zeros. Put y final, which we know, and minus y naught, again, which we know, equals v naught magnitude sine of theta t minus 1/2 gt squared. Cool. So now if I go through and look, same thing, same song and dance. I have a value for final, I have a value for initial. I don't know v naught, I don't know t, and I don't know t. And you notice I have underlined the exact same two variables. I have two unknowns and two equations. I can substitute and solve. So this is what we mean by solving simultaneous equations. We have to actually get the two equations and substitute them together to finally figure out the answer. Now, you see this one has a quadratic, and so to actually isolate t by itself here, I'd have to do some sort of funky quadratic formula or something like that. Actually, I'm going to take this one. I think I'm going to... Do I want to rewrite it? I think I'm going to rewrite this one, actually. I'm actually going to solve this for v naught. So I will swap the positions of t and v naught. Do something like that. Now if I take this and I'm going to substitute it in right here for v naught. So usually how I do this is I'll do something like sub. Okay. Notice I've used the x direction in one column, the y direction in another column, and if I take a value, I'll do an arrow just to sub it over, just to help try to guide you with what I'm doing. So then I have y final minus y naught equals x final divided by t cosine of theta sine of theta times t minus 1/2 gt squared. And hopefully you notice, oh goody goody, I don't actually have to solve a quadratic equation. I've got a t in the numerator here, which cancels the t in the denominator there. Say furthermore, sine of theta divided by cosine of theta, that can be written as the tangent of theta. So I have y final minus y naught equals x final tangent of theta minus 1/2 gt squared. I'll let you go ahead and solve, but what we're looking for is an expression for t. Good. So what I'll do, I'll write this as 1/2 gt squared equals x final tangent of theta minus, put y final minus y naught. And then I just have to get rid of this. So I get t squared is equal to 2 over g x final tangent of theta minus y final plus y naught. And of course, we have to take that whole rigmarole and square it. So we take a square root. Good. Now the last step, because we're not asked to find the flight time, though we could. The last step was we were asked for the speed. And so we'll have to take this and substitute it back in. to sub it back in. So, ooh, not going to be pretty, right? So this would give us, if I look, this gives us x final times the square root of g divided by, put cosine theta, actually, yeah, times 2 x final tangent theta minus y final plus y naught. And that would be to the 1/2. Technically, that's it. We now have, excuse me, let me put, technically, that's it. We now have the expression that we wanted to find the initial speed. What we have to do here is actually plug in numbers. Now, I know this expression looks, ugly, but please keep in mind that we just went through a couple of simple algebraic steps to actually arrive at it. Okay, that's the first one. The second one is, let's go ahead and clear off the rest of the table. Guess I could have, let's clear this off. And I'll actually clear this all off too. Okay. And let's take a look at this expression and see if it can pass some of our sanity checks. Okay. So what are some good sanity checks? Well, for example, you can think of how fast, I know we're told the angle, we're told it's 30 degrees. But let me ask you this, if the angle were 0 degrees, if theta were 0 degrees, how fast would you have to hit the ball in order to get it over the wall? It doesn't matter how fast you hit it, it won't go over. So something goofy should happen here if I put in 0. Okay? So let's go ahead and take a look. What happens if I put in 0 degrees into this expression? Something goofy should happen because from a physics standpoint, from a physical, just thinking about hitting a home run, if I hit the ball at 0 degrees, there's no way that it'll ever get over the wall. Let's see what happens here. So you can play it in your mind if you want. I'll actually write it out so that we can follow along. Okay. Well, x final divided by the square root of g, that doesn't involve the angle, so that stays the same. Cosine of 0 is 1. So I put 1 here. So I get the square root of 2. Okay, got the cosine. And then let's deal with this term in the parentheses. Well, x final just stays that. Tangent of 0 is 0. So I end up with a 0 here. This is just 0. 0. And then I get minus y final plus y naught. And now maybe you'll say, well, I don't see anything goofy there, Greg. And I say, ah, yes. Let me ask you this. Which one's larger, y final or y initial? In our case, y final is larger. So if I look, this term, y final is larger than y initial, and therefore this term is less than 0. And now hopefully you see the problem. I have a number that's less than 0 and I take a square root. And from what we're dealing with right now, that's a no-no. You can't do that. In other words, it is not possible to apply this expression if the launch angle were 0 degrees. Okay? It protects you. Sometimes when you see a no-no in the math, it's saying this physics problem is not, you can't do it. It's not possible. Okay? So at least this works out. There's some sort of goofiness if we launch at 0 degrees. In fact, we could go a step further. There is some angle, some minimum angle, right? You have to make sure that this term in the denominator, this square rooted term, you have to make sure it's greater than 0. So there's a condition. In fact, no, okay. Let's do this. Let's do the sanity checks first, and we'll come back to that condition. Huh? What other sanity checks do we have? Well, here's another one. Let's say that you hit the ball straight up. Let's say theta were 90 degrees. Then what would happen? We should, again, run into some sort of, this isn't going to work. It's a no-no. Let's see where it is. So again, V naught equals, well, our numerator's still fine. Nothing happens there. And we look at our denominator. Cosine of 90 is 0. All of a sudden, we see, okay, well, I could do the rest of this, but at the end of the day, cosine of 90 is 0. And that is a no-no. Division by 0. Not possible. So again, we have two cases here, theta equals 0 and theta equals 90, where you can't come up with a speed because it's not physically possible. Just like what you would expect. If I pop a ball straight up, there's no way it's going to get over that outfield fence. Good. So I say that these are sanity checks, okay? It's taking what you know from thinking about the situation and seeing if the equation applies or if the equation gives you the expected result. And generally, that is very useful thinking about extremes. So really small numbers, really large numbers. Okay? In this case, I thought about the extremes. 0 degree launch, 90 degree launch. Okay? Let's think, well, for example, what would we expect if the ball were real, or if the wall, x final, were really, really large? In other words, the wall is really, really far away. We would expect that the speed that you hit the ball should go up. Okay? So again, let's think about what happens in the limit as x final goes to infinity. What do we get? Well, we get a really big number multiplied by some number. And if you're familiar with how to do limits, you can basically, okay, nothing changes here. Okay. Down here, you get cosine of theta. You have the square root of 2, so I'll keep the factors 2. Now here, I get a really big number and a really small number added to it, right? X final is going to infinity. If I add a small number, it's still basically infinity. So I can throw out that stuff. So I just end up with x final tangent of theta to the 1/2. And we'll keep going. Notice I have an x final here, and a square root of an x final. So that should give me a square root of x final in the numerator. Okay? So as x goes to infinity, as the wall gets further and further away, apparently the speed that I need to hit the ball at is x final g square rooted divided by the square root of 2 cosine of theta tangent of theta square rooted. And this again behaves as we expect it. At least as x final gets further away, as the wall gets further away, I have to hit it faster. Okay. Now, none of these will actually tell you that this is the exact expression to use. All of these sanity checks are a way of making sure, how would I say it? Sanity checks do not tell you that you've done a problem correctly. They will definitely tell you if you've done it incorrectly. Okay? So the fact that it's passed all of these sanity checks doesn't mean that I have the right answer. What it does mean is the more sanity checks that it passes, the more confident you can be that the answer is correct. Okay, so what we're doing is building confidence in our answer. And I'm sure you've had this. Did I do the problem right? I don't know. How can I check? This is one way to check. Check, in quotes. Okay, this, as you do your sanity checks, this helps build confidence that indeed you have the right answer. The equation performs the way you expect it to. Okay. Well, without any further ado, I guess we should probably actually substitute in some values, right? So let's go at this. We have something that says, okay, well, what speed do we actually have to shoot this thing at? We said x final was 94.5, and we have 9.8 square rooted. Okay. Cosine of 30 degrees, square root of 2, 94.5 tangent of 30 degrees, minus, we'll say y final is 11.3, and I'll say that we hit it from, I don't know, 1 meter in height. So say at the batter's waist. Okay. Well, plug and chug. Good. Okay, so I went through and I've got the number. Well, I got a number. I got 36.3 meters per second. Cool. So to hit a home run at 30 degrees, you need to hit it at 36.3 meters per second. Hopefully you got the same answer. So I'll leave it there for right now. I'll recap. We had two problems. The first one being a projectile motion where we used the distance in the y direction to find the free fall time, and that allowed us to calculate the speed in the x direction. Here, the second problem, we had a slightly different situation. We didn't know two things, and we weren't able to actually isolate, say, one component to get the time and then the second component to get the speed. What we had to do was actually work in terms of variables and solve simultaneously the two equations. Now, if you wanted to, you could indeed go back and figure out the flight time if you so choose. Okay? I'll leave it there for right now. Please bring questions to class. Thank you for your attention. I'll see you next time.